Okay, hello everyone, in a new video. In this one we are going to solve exercise number 10, page 87 in chapter 4, which is the chapter of mechanical actions. The title of this exercise is studying the elongation of a spring. A spring with initial length L0 is equal to 40 centimeters is suspended vertically. It's attached by its upper end to a fixed support. So this is the spring. Here on the left we have a graduated ruler. So from the graduated ruler we can find that the length of the spring is given by L0 is equal to 40 centimeters. And this is the support. Okay. Now in part A they are telling me a person pulls vertically down the free end A of the spring with a force of 5 newtons. So here this is the hand of the person. So the person pulls the spring vertically downward with a force of magnitude 5 newtons. Then the spring elongates. Okay. Now in 10.1 they are asking me about what are the characteristics of this force, the force exerted by the hand of the person. So characteristics of the force. We know that the characteristics of the force are given by the point of application, the line of action, the direction, and the magnitude. Whenever they ask us about the characteristics or the properties of the force, we need to list them in this order, which is given the point of application, line of action, direction, and magnitude, which is given by the Pildim. Now let's specify these properties. The point of application is the point of contact A. And the line of action, so notice that here they are telling me that the person pulls vertically down. So this is the vertical and this is the horizontal, and it's clear that from the figure that the person is pulling vertically downward. So the line of action is vertical, and the direction, as we have said, it is downward. And the magnitude here it's given to be 5 newtons. Now in 10.2 they are telling me reproduce the figure and represent this force using the scale 1 centimeters for 2.5 newtons. And by represent, it means that we need to draw this force, the force due to the hand of this person exerted on the spring. Now in order to represent this force, we need to know the length of this force, knowing that its magnitude is 5 newtons. Our rulers are graduated by centimeters and not newtons, therefore there must be an equivalence between centimeters and the newtons, and this is given by the scale. Then each 1 centimeter corresponds to 2.5 newtons. As for 5 newtons, it corresponds for 1 multiplied by 5 divided by 2.5. So here we do cross multiply. 5 multiplied by 1 divided by 2.5. This will give us 2 centimeters. Then the length of this factor according to this scale is given by 2 centimeters. So this is the point A. The force F is being applied at the point A vertically downward like this. So the length of this factor is given by 2 centimeters worth of 5 newton. So they didn't name this vector, no need to write its name. Now in 10.3 they are telling me by referring to the figure what's the length L of the spring. And here we must be very careful. They are asking me about the length L of the spring. here one could answer that the length of the spring is given by 40 centimeter, but notice that the 40 centimeter they are naming it to be the initial length, so they are not asking me about this length. And now one could answer that the length of the spring is given by 10 centimeters, which is the difference between 50 and 40, and this answer is also wrong because this is not the length of the spring, this is the elongation. So here, by the length L of the spring, they are asking me about this length, which is 50 centimeters, which is the final length of the spring. So in this case, the length L of the spring from this figure is given by 50 centimeters. Now in 10.4, they are telling me what's the elongation delta L, which is given by L minus L0 undergone by the spring. So we already know the value of L, which is given by 50, and we know the value of L0 here to be given by 40 centimeters. This will give us 10. Now since 40 is in centimeters and 50 is in centimeters, so the value of delta L will be in centimeters. We know that centimeters is not the SI unit of length. In order to convert from centimeter to meter, because we know that meter is the SI unit of length, we divide by 100. Therefore, 10 centimeters divided by 100 will give us 0.1 meters. So the elongation delta L in this case, when it's applied to the force of 5 Newton, is being elongated by 0.1 meters. So delta L in this case is equal to 0.1 meters. Now in part B, the spring is now successively subjected to successive forces. The results are given in the following table. So here, let me write that delta L is equal to 0.1 meters, corresponds to F is equal to 5 newtons. Let me make some space here. Then now we are in part B of this exercise. They are telling me in 10.1, copy the table again and complete the empty boxes. So this table consists of 3 rows. In the first column we have the magnitude of the force F in newtons, we have delta L in centimeters, and in the final row we have the ratio between F and delta L, in which F is in newton and delta L in centimeters. Now we can complete the following table. We can complete this box, this box, this box. In order to complete this box, first we need to complete this empty box. So in this one here, they are telling me that F is given by, so the value of F in newtons is given by 5. What is the elongation delta L in centimeters? So always whenever the exercise consists of 2 parts, part A and part B, we should always keep in mind that both of these parts are related to each other, so we will use the result of the first part and the second part. So here in the first part, when the force F was 5 Newton, we have determined the elongation delta L to be 0.1 meters or 10 centimeters. So from the first part of this exercise, we can know that for F is equal to 5 newtons, the value of delta L is given by 10. And here we don't include any unit because the unit is included in the first column. Now we can safely complete the third row of this table. So dividing 5 by 10, this will give us 0.5. So 10, we are in part 2.10.1. Dividing 5 by 10 will give us 0.5. So here 0.5. 10 by 20 will give us 0.5. 15 by 30 will give us 0.5. As well, for 20 divided by 40, 0.5. Now in 10.2, they are telling me by using the results obtained in the table, deduce that f and delta r are directly proportional. Notice that here in the third row, the value of f over delta remains constant, which is given by 0.5. Then let's say since f over delta L remains constant, and it is given by 0.5, then we can say that f over delta L is equal to 0.5. Now we are ready to answer whether f and delta r are directly or inversely proportional. To do so, we need to put f on one side and delta L on the other side. So in this case, let's keep f on the left and take delta L to the right. So here f over delta L and 0.5 is divided by 1. Then crisscross delta L, if you want to take it to the right, because it's below, then moving it to the right, it will be above. Then f is equal to 0.5 multiplied by delta L. So notice that here f and delta L, both of them are above on the same side. So in this case, they are directly proportional. Then f and delta L are directly proportional. Now in 10.3, they are telling me draw on a graph paper the graph giving the variations of the force F as function of the elongation delta L. Given that the scale on the horizontal axis is 1 centimeter corresponds to 10 centimeters, and on the vertical axis 1 centimeter corresponds to 5 Newton. Let me make some space here. So always whenever we need to draw the graph, first we will draw the system. So this is the x-axis and this is the y-axis. And the next step is to label correctly the x-axis and the y-axis. So notice that here they are telling me the variation of the force F as function of the elongation delta L. So the first variable that comes after the variation is given by the force F, then this will be on the y-axis. So here we will put the variable F or the quantity F on the x-axis we will put the elongation delta L. Now from the table, the force F is given by newtons and delta L is given by centimeters. Now let's write the scale. Here the scale is given by, let me write the scale here. The scale is given by each 1 centimeter corresponds to 10 centimeters. This is on the horizontal axis. So for each division, we will add 10 centimeters starting from the origin. This is 10, this is 20, this is 30. Now we will stop at 40 because it's the largest value included in the table. This is 40, so no need to continue. And as for the vertical axis, so this is the vertical and this is the horizontal. On the vertical axis we have each 1 centimeter corresponds to 5 Newton. Then on the vertical axis, for each 1 division or 1 centimeter we'll add 5 Newton. So this is 5, 10, 15, 20. We will stop here because the largest value of F included in the table is 20. Now let's locate the points. For 10 centimeters, the value of F is given by 5. For 20, the value of F is given by 10. For 30, the value of F is given by 15. And as for 40, The value of F is given by what? 20. And we connect these points using a ruler, not by our hand. And as we can notice that it is a straight line passing through the origin. And we don't forget the title. We can extract the title from the question, which is given by the variation of the force F as function of the elongation delta L. So the variations of the force F as function of the elongation delta L. So usually they give half a mark, or half a mark for the labeling of the axis to be correct, and for dividing this axis, 1/4 for the title and 1/4 for the scale, and for example half a mark for drawing the graph to be correct. Now in 10.4 they are telling me what's the shape of the obtained curve. So notice that this is the curve, and the shape of the curve is a straight line, and it's not enough just to say that it is a straight line. We need to say that this straight line is passing through the origin, or passing through the origin. Now in 10.5 they are telling me determine graphically the magnitude of the force F that produces an elongation delta L is equal to 24 centimeters. So here we need to refer to the graph or to the curve in order to determine the magnitude of the force F corresponding for delta L is equal to 24 centimeters. And here let's write it graphically. And they usually give a half a mark for mentioning this word, which is graphically. For delta L is equal to 24 centimeters, we are interested in calculating the value of F. So notice that delta L is equal to 24 centimeters doesn't appear here in the table. We need to refer to the graph in order to determine the value of F by referring to the curve. So this is 24. Going up to the curve, it corresponds to this point on the curve. Then going to the F axis, so this is given by 12. Then we have that F is equal to 12 newtons. And now in part 10.6 they are telling me determine graphically the elongation delta L of the spring for a force of value F is equal to 18 newtons. So we need to refer to the curve or to the graph. Then let's say graphically. And I repeat, they usually give half a mark for mentioning this statement. So for F in this case is equal to 18 newtons, we need to refer to the graph in order to determine the value of delta L. We have delta L is equal to 2. To what? So this is 18 centimeters here. Now it corresponds to this point on the curve. Now going to the delta L axis. So here delta L is equal to 36 centimeters, which corresponds to F is equal to 18 newtons. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.